Let me show you what I would like you to know about our A&P lab exercise 8 on bone tissue and long bone growth. This first image from our laboratory manual in exercise 8 shows the bones of the skeleton, which is our sort of subject for this whole part of the lab manual. And this first illustration shows the most general classification of all the bones in the skeleton. We're going to classify it into two parts, which make up the lab exercises 9 and 10. The axial skeleton drawn in green, the skull and the spinal column, and the bony thorax, the rib cage, the ribs and sternum. And then the appendicular skeleton represents the appendages, the limbs, the arms and legs, and the girdles, they're called, that attach them to the axial skeleton. So everything drawn in tan. So those are the two most general classifications. And you should know the names of all the major bones of the skeleton, and most of them are listed right here in this drawing. We also have a little review skeleton cartoon showing the three types of cartilage. And I would like you to also remember where those are located in your body and a little something about their properties. So it's a good review. Hyaline cartilage has the finest collagen fibers in its extracellular matrix surrounding the chondrocytes and their lacuna. And in fact, it's so fine that when you look at hyaline cartilage histological sections, you can't really see the fibers. You just see an amorphous sheen of gray or pink color around the lacuna. So here we find hyaline cartilage in the bridge of the nose, attaching the ribs to the sternum, the costal cartilages, and on the ends of long bones, the bones of your appendages, where there's freely movable joints, the bones are all covered with a layer of hyaline cartilage. It's very, very smooth, and with a little lubricant, it makes the joints be able to move with little or no friction. Also, your larynx, your so-called voice box, and your Adam's apple there, it's like a box of hyaline cartilage with your vocal cords inside, and all the airways in your lungs, down to nearly the smallest airways, have rings of cartilage in the wall to keep them open so that air flows most easily through them. Secondly, elastic cartilage has a lot of elastic fibers instead of collagen fibers, but still has chondrocytes in their lacuna. The pinna of your ear, you can grasp that and feel its properties and distinguish between elastic cartilage and feel the bridge of your nose and that stiff feeling, flexible but stiff feeling of hyaline cartilage. Also, there's elastic cartilage in your epiglottis, a little valve that folds down and covers over your larynx, your voice box, every time you swallow, so that liquids and solids from your oral cavity travel posteriorly into the esophagus rather than down into the trachea. And then finally, fibrocartilage forms joints called symphyses. The pubic symphysis there, it's a strange word. I don't know if it's on this slide. symphysis, symphysis. Anyway, there's a little bit of fibrocartilage between the pubic bones there. There's fibrocartilage in between your vertebral bones. The intervertebral discs are made of fibrocartilage, cylinders of fibrocartilage between the bodies of the bones. And then finally, there's a pad of fibrocartilage in your knee. The meniscus of your knee is a slab of fibrocartilage on either side of the flat plane-like tibia for the two joint surfaces of the femur. All right, here's a little cartoon, our first introduction to kind of the arrangement in bone tissue using a long bone as an example. Long bones are the bones, again, of your limbs, and they're skinny bones, very stiff and strong, with a kind of a bulbous head on either end. We're not going to call it a head ever again. We're going to call these enlargements on the proximal and distal ends epiphyses. Partly because it's good to use whenever we learn some new vocabulary, you should stick to that. Use technical language. We're going to be science about it. The other thing is, as we'll discover later, particular specific ends of individual bones in your skeleton are formally called the head on one end or the other. So we don't want to just call the ends of bones' heads, because we'll get confused about which bones in which the epiphysis is named the head and which epiphysis is not named the head. So proximal epiphysis and distal epiphysis, away from the torso. Diaphysis is the name that you should use forever after about the shaft of the bone. And in adults, the diaphysis is hollow. There's a cavity in there called the medullary cavity, back to that same terminology to describe the inner part of some anatomical structure, and it's filled with yellow bone marrow, which is just fat, adipose tissue. A little reservoir of some energy store right in there in the bone marrow in the medullary cavity. We can see some different distinct arrangements of bone structure. The wall of the diaphysis, which we can see here and here also, is very compact or dense, and that's great because the name of this type of bone tissue is compact bone. And it is in fact compact. There's lots of stuff there. The building material is really structurally strong and dense. Then we see spongy bone in the epiphyses, and we'll see also in flat bones, we'll see some spongy bone. And the spongy bone is the site of red bone marrow. So wherever you see this kind of arrangement, this appearance of like little air cells or holes, there's red bone marrow in there, which is the site of blood cell synthesis. So all the red blood cells and white blood cells come from spongy bone, location of red bone marrow. Okay. The surface of the bone has a covering on it, protective covering on it, and as we said, on the ends of bones where the joints form, the movable joints form, there's a layer of hyaline cartilage. That's called articular cartilage because articulations are joints. It reduces friction. Wherever there isn't articular cartilage, the bone is covered by a dense, irregular connective tissue type fibrous covering called the periosteum. Peri meaning around, osteum meaning a bone. And so here's the periosteum. It's been kind of peeled back, and it shows that it's anchored to the bone tissue itself by some very heavy collagen fiber bundles called Sharpie's fibers. Now let's look in on the compact bone a little more closely, so we can see how compact bone is constructed and learn some terms associated with some of the structures we see there. So here is a cartoon showing part of the wall of the diaphysis of a long bone. And we can see that the structure of a long bone is a package or a series of long cylindrical units. So each one of these cylindrical units extends the length of the diaphysis, and many of them bundled together forms a very strong, stiff tissue indeed. So these individual units are called osteons. That's one unit of compact bone. It's also called a Haversian system. That's a proper name for this whole thing. They've made a telescope out so we can see that osteons are made up of concentric cylindrical layers of tissue. And another name for compact bone, proper formal name for it, is lamellar bone, and lamella are just layers. So lamellar bone has lots of layers. So all these osteons are packaged together, but then there's got to be something to fill in the space in between, and so there's some bone tissue in there that is called interstitial lamella, some bone tissue that fills in the gaps between these cylindrical osteons. And then finally, the diaphysis is encircled by, enclosed by some layers, some large, circumferential layers of bone tissue called circumferential lamella, or layers. So that's the kind of arrangement of things. Let's look a little closer at some of the features of the osteon, where you see the little yellow barbed wire looking effects. Those are the lacuna of compact bone. So here we see it too. At the boundaries of each layer of an osteon are lacuna, and in those lacuna reside osteocytes, bone cells. They're the cells that maintain and renew the bone regularly throughout your lifetime. So osteocytes in their lacuna form these cylindrical layers. In the center of each osteon is a hollow canal called the central canal through which blood vessels pass and nerves, and this is a highly vascular tissue, and hence probably it's highly regenerative, or for whatever reason it's a highly regenerative tissue. So we have osteocytes in the lacuna, but we have under the periosteum and actually also under the endosteum, a very fine connective tissue layer on the inside surface of the bone, lie osteoblasts. Osteoblasts are embryonic-like cells that can synthesize new bone tissue from scratch. If you damage the bone, break the bone, the osteoblasts will become activated and start secreting bone matrix and produce a repair that is stronger than the original bone. So that's the osteoblasts. They're bone makers. Under the periosteum also are osteoclasts, which are cells that can dissolve the extracellular matrix, specifically the inorganic part of it. So the extracellular matrix of bone is made up of collagen, just like in connective tissue proper oftentimes, just like in cartilage. So we have three tissue types that are made all of the same basic material. They're largely made up of collagen fibers, but the ground substance in bone is a mineral-like hydroxyapatite, it's called, and it's made of calcium phosphate crystals, and it's very, very hard and stiff. So we take collagen fibers, and instead of immersing them or surrounding them by proteoglycans of various types, we have now surrounded them by a hard mineral, and so the ground substance has completely changed the properties of this tissue into this familiar, rigid, stiff, hard character of bone. Pretty cool. But anyway, osteoclasts can dissolve that hydroxyapatite mineral component of the ground substance and release calcium into the blood. So those guys are the homeostatic effectors that can maintain the blood calcium concentration, and we'll talk about that another time. Also, there's some perpendicular passageways through which blood vessels can enter into the central canal of osteons or cross from osteon to osteon. They're called Volkmann's canals or perforating canals. Here's a micrograph of a preparation called dry ground bone. It's not so easy to produce a micrograph of a thin section of bone the way it is with most of the soft tissues, where you just need a very, very sharp knife and a special machine that can make for some very thin slices, slap them on a slide and stain them and take a look. Well, bone is hard, and so it's a little not quite so easy to do that. So anyway, this, I don't even know exactly how they do it, but dry ground bone looks like this, and it recapitulates the cross-sectional look of these osteons and all of their layers. All the little dark smudges there in circular arrangement represent the lacuna containing osteocytes, bone cells, at the boundary of each of the lamella or layers of these osteons. And here you can see some interstitial lamella in here with their osteocytes in their lacuna. The central canals are evident, readily apparent in this micrograph. This is I picked this particular micrograph because it happened to contain a Volkmann's canal, a canal perpendicular to the central canal, where blood vessels would be entering into this osteon here. So you can't really miss that structure, or that histological section. That's an important one to know when you see that slide, to know what it is. Another way of getting some information in representing an osteon is by drawing in kind of the grain or the arrangement of the collagen fibers that make up each lamella of the osteon. So we can see that the heavy-duty collagen fibers here are arranged in a spiral fashion in each one of the lamella, and then each lamella has a perpendicular or opposite direction spiral of the fibers, so that when you then immerse this thing in a rigid cement-like mineral, makes for an incredibly strong overall structure. You can see the blood vessels and nerves in the central canal there. So the collagen fibers are referred to as the organic component of the bone, and the hydroxyapatite is the inorganic component. And here's another micrograph showing the osteocyte and its lacuna. And in this slide especially, you can see the canaliculi, microscopic canals that look just like little scratches in this micrograph. But they're actually little passageways that emanate from the central canal out to all of the osteocytes lacuna, so that they can receive. There's a liquid flowing in those chambers, in those canaliculi, that carry nutrients and oxygen to the osteocytes. I don't know if it's flowing per se, but there's diffusion happening in there that carry those nutrients in. Decalcified bone. This slide, I probably won't ask you to look at a slide of this anytime. I'll post some slides for you on the mastering site, but I did want to point out something pretty cool about this. This is a picture of bone forming, flat bone forming within a fibrous connective tissue membrane in the fetus or in the newborn. And this row of cells here on the surface of the newly forming bone within this, which essentially is dense irregular connective tissue, are osteoblasts. So there's a layer of osteoblasts which will eventually, when this bone is complete, this flat bone is complete, will be covered over by the periosteum. But there'll be still all this row or layer of osteogenic layer of osteoblast cells along the surface of the bone tissue. And you can see some osteocytes when the bone cells become trapped in among the extracellular matrix of bone. As the bone continues to develop and grow, they become osteocytes. This slide is going to lead us into looking at how long bones grow longer. It shows some hyaline cartilage. The characteristic look of a micrograph of hyaline cartilage, you can see again, is this amorphous gray material, which is the extracellular matrix of cartilage, with collagen fibers so fine you can't really identify them individually. And then you can see chondrocytes. Now we're switching over to cartilage. Chondro meaning of cartilage, chondrocytes in their lacuna. This is the wall of the trachea, and it's kind of an unusual choice of a micrograph because it shows the curvature of the trachea, the opposite of what you'd expect. Typically you'd see a rounded portion of a circle represented by the trachea. So anyway, that's how hyaline cartilage looks, and here's how it looks in the epiphyseal growth plate. In bones that are still growing in length, bones of, say, the child or the young adult, very, very young adult, teenager and so forth, there's a slab of hyaline cartilage between the diaphysis of a long bone and the epiphysis. So the epiphysis would be here. It's not shown in this picture. But in between the two is a joint called the epiphyseal growth plate. And the majority of this slab of cartilage, hyaline cartilage, looks like any hyaline cartilage. We're at a little lower magnification, but it's mostly just hyaline cartilage, and it's called reserve cartilage. But if we move our gaze closer and closer to the diaphysis of the long bone, in this growing long bone, we see some dynamic things happening. We see columns of chondrocytes appearing because the chondrocytes are dividing by mitosis, and as they do so, they are creating new cartilage matrix, and the cartilage is getting thicker and thicker, pushing the epiphysis up and away from the diaphysis. And as those columns of chondrocytes continue to form, as we look closer to the diaphysis, the chondrocytes are enlarging, and they're dissolving away some of the cartilage matrix around them, so that the columns become closer and closer together, and eventually the chondrocytes die, and there's nothing left but a dangling fringe, remnants of the hyaline cartilage tissue that was present here in the growth plate. On those spicules, they're sometimes called, of dangling hyaline cartilage, calcium phosphate crystals begin to form. And this is called the zone of calcification. I should have highlighted that when the columns of chondrocytes form by cell division, that's called the zone of proliferation. When the cells begin to enlarge and the columns draw near to each other and there's only some thin columns of cartilage tissue, extracellular matrix left. That's called the zone of hypertrophy, because hypertrophy means to grow larger, and the cells are getting larger and the lacuna are getting larger. Anyway, the zone of calcification is here, and then osteoblasts come in and secrete bone matrix and create brand new spongy bone on the surface of all those dangling fragments or remnants of cartilage, and we have brand new bone forming here in the diaphysis. So what's effectively happening is the epiphysis is thickening and pushing, or the growth plate is thickening and pushing the epiphysis away from the diaphysis, making the whole overall unit structure longer. But then at the face of the growth plate and the long bone diaphysis, we're forming new bones. We're chewing off the new part of it at the epiphysis, at the diaphysis face of the plate, and we're building up the plate further away from there. So I hope that's not too confusing the way I've stated that. So that's how long bones grow longer, thickening the growth plate and then forming bone on the diaphysis surface. Eventually, during the growth of the adolescent, the growth plate gets thinner and thinner and thinner until eventually there's nothing left but a line of what looks like compact bone, the epiphyseal line. So if we go all the way back to our cartoon of the bone, we see this dense line right here between the epiphysis and diaphysis. This is a remnant of what was previously the epiphyseal growth plate. This bone has finished growing. Once the epiphyseal growth plate, quote unquote, closes and it forms a bony epiphyseal line, the bone can never grow longer again. So the growth period in life occurs when the growth plate is still active with some hyaline cartilage, and then right about your age, the last of the growth plates are closing and all of your bones have reached their longest extent that they can. Here's another micrograph just showing the zone of proliferation, the zone of hypertrophy, the zone of calcification, and then the osteogenic zone, if you want, where the new bone is forming. I chose to add a different micrograph in here because you can't really see any reserve cartilage in there, and I wanted you to see some just plain old run-of-the-mill hyaline cartilage, which makes up the majority of the growth plate here. So that's the end of our discussion of bones. When we get into the lab, we'll examine some bones so we can isolate the properties of bones that are contributed by the organic component, the cartilage, the collagen fibers, and the inorganic component, the hydroxyapatite crystals. So join me in the lab as we talk about a little bit more about bone.